Magnesium was reacted with hydrochloric acid in excess according to the following equation. 1 mole of magnesium reacts with 2 moles of hydrochloric acid to produce 1 mole of magnesium chloride and 1 mole of hydrogen. When 0.0354 grams of magnesium was reacted, 35.63 milliliters of hydrogen gas were collected at 20 degrees Celsius and 99.5 kilopascals. The partial pressure of water vapor at 20 degrees Celsius is 2.333 kilopascals. Solve questions A to E. A. How many moles of magnesium were reacted? First, we need to determine the molar mass of magnesium, which we can obtain from the periodic table. The molar mass of magnesium is 24.31 grams per mole. Next, we need to create a proportion consisting of ratios of grams of magnesium to moles of magnesium. Our first ratio should consist of known values, and the known values are 24.31 grams and 1 mole. The other ratio should consist of a known value and an unknown value. The known value is 0.0354 grams of magnesium, which is given in the question, and our unknown value is X, which represents the moles of magnesium corresponding to 0.0354 grams of magnesium. Next, we need to solve for X by cross multiplying. 24.31 times X equals 0.0354 times 1. 24.31x equals 0.0354. Therefore, X equals 0.0354 divided by 24.31. X equals 0.00146. Now we need to write this number in scientific notation, which is 1.46 times 10 to the power of negative 3. Hence, 1.46 times 10 to the power of negative 3 moles of magnesium were reacted. B. How many moles of hydrogen were collected? In the previous question, we have calculated that 1.46 times 10 to the power of negative 3 moles of magnesium reacted. Now, from the balanced chemical equation, we can see that 1 mole of magnesium produces 1 mole of hydrogen. Hence, 1.46 times 10 to the power of negative 3 moles of magnesium produced 1.46 times 10 to the power of negative 3 moles of hydrogen. C. Calculate the partial pressure of hydrogen gas. Note, the gas collected contains hydrogen gas and water vapor. So, you need to determine the partial pressure of the hydrogen gas. Now, we need to use Dalton's law of partial pressure, which states that the total pressure of a gas is the sum of the partial pressure of each individual gas. So, in this case, the total pressure equals the partial pressure of hydrogen plus the partial pressure of water vapor. So the partial pressure of hydrogen equals total pressure subtract partial pressure of water vapor. Now both the total pressure and the partial pressure of water vapor given in the question. The total pressure is 99.5 kilopascals and the partial pressure of water vapor is 2.333 kilopascals. So substituting values, partial pressure of hydrogen equals 99.5 subtract 2.333 equals 97.167. Hence, the partial pressure of hydrogen is 97.167 kilopascals. D. Determine the molar volume of hydrogen gas at standard temperature and pressure. Now first, we need to determine the volume of 1.46 times 10 to the power of negative 3 moles of hydrogen gas at STP. Then we need to determine the molar volume, or the volume of 1 mole of hydrogen gas at STP. D. Step 1. Determine the volume of 1.46 times 10 to the power of negative 3 moles of hydrogen gas at STP. Now we need to use the combined gas equation, which is P1V1 divided by T1 equals P2V2 divided by T2. Let P1, V1, and T1 be experimental values. P2 is the standard pressure, T2 is standard temperature, and V2 is the calculated volume of 1.46 times 10 to the power of negative 3 moles of hydrogen gas at STP. Now we need to rearrange the formula to determine V2. Therefore, V2 equals P1 V1 T2 divided by T1 times P2. Now, P1 is the partial pressure of hydrogen gas that we have calculated in C. So from part C, we can see that the partial pressure of hydrogen is 97.167. V1 is the volume of hydrogen gas collected. Now V1 is given in the question. It is 35.63 milliliters. Now we need to convert this value to liters by multiplying the value by 10 to the power of negative 3. T2 is the standard temperature. It is a known value of 273 Kelvin. T1 is the temperature at which the hydrogen gas was collected. This value is given in the question, and the value is 20 degrees Celsius. Now we need to convert this value to Kelvin by adding 273. And finally, P2 is the standard pressure, which is a known value of 101.3 kilopascals. Now substituting values, V2 equals 97.167 times 35.63 times 10 to the power of negative 3 times 273 divided by 20 plus 273 times 101.3. Now using your calculator, you will find out that V2 equals 0.031 liters. Hence, the calculated volume of 1.46 times 10 to the power of negative 3 moles of hydrogen gas at STP is 0.031 liters. D. Step 2. Determine the molar volume of hydrogen gas at STP. Now we need to use this formula. Molar volume equals volume of gas at STP divided by number of moles of gas. Now the volume of hydrogen gas collected at STP was calculated in D step 1. So in D step 1, we can see that the volume of hydrogen gas collected at STP was 0.031 liters. And the number of moles of hydrogen gas was calculated in B. So in B, we can see that the number of moles of hydrogen gas collected was 1.46 times 10 to the power of negative 3. So substituting values, molar volume equals 0.031 divided by 1.46 times 10 to the power of negative 3. Using your calculator, you will find out that the molar volume equals 21.23. Hence, the molar volume of hydrogen at STP is 21.23 liters. E. The formula for percent error is percent error equals experimental value subtract theoretical value divided by theoretical value times 100. Determine the percent error of the experimental molar volume of hydrogen gas determined at STP. Now, the experimental molar volume of hydrogen gas at STP was determined in the previous step. In D step 2, we have determined the molar volume of hydrogen gas at STP, and it is 21.23 liters. Now, the theoretical molar volume of hydrogen gas is known. It is 22.4 liters. So substituting values, percent error equals 21.23 subtract 22.4 divided by 22.4 times 100. Using your calculator, the percent error equals negative 5.22%. Hence, the percent error of the experimental molar volume of hydrogen gas determined at STP is 5.22%.